Okay, welcome back. Now that we've been through intermolecular interactions and intermolecular forces, a few other issues we want to kind of tie up to finish up the material in Chapter 10. Now, most of these relate to phase changes, which of course we can relate pretty easily to our types and strengths of intermolecular interactions as well, but a few more things we want to think about, and also ways we can kind of calculate what's going on during a phase change here as well. So the first thing I want to talk about, just because there are some misconceptions that pop up occasionally, is terminology that we would use for a phase change. So we're going to focus on the three main states of matter, which would be solids, liquids, and gases. And there are other states like plasmas, but they really aren't relevant to what goes on in kind of everyday chemistry, so we're not going to worry about those. Now, if we take a solid and we convert it into a liquid, that is a process known as melting, right? And sometimes we'll hear about the temperature at which this occurs referred to as the melting point. Now, an important thing to keep in mind is the liquid becoming a solid is just the reverse of that process. So we use a different term there, freezing, and we might refer to that temperature as the freezing point, but those are the same temperatures. The melting point and the freezing point are the same for a particular material. So we would use either term interchangeably, and don't get confused if you think something is melting but you hear it described as a freezing point, because those are happening at the same point on a temperature scale. Now, a liquid to a gas, if a liquid becomes a gas, there's a couple terms that will be used there. One is boiling, and the other is evaporation. Now, either one of those is appropriate. The difference there would usually be the temperature. If you're at the boiling point where the liquid will turn into a gas, you would describe that as boiling. But we will see that a liquid can turn into a gas below that temperature, which we would be more likely to refer to as evaporation. Now, if a gas turns into a liquid, this is referred to as condensation. This is what happens when steam, you're cooking pasta, and steam from the boiling water gets on the inside of your window and condenses into water. Okay. Now, solids and gases can also interconvert as well. When a solid becomes a gas, this is a process known as sublimation. And there's a few fairly common Gen Chem experiments where you may sublime a solid into a gas and then catch it on a cold surface, like naphthalene does this, the active ingredient in mothballs we often use in some of our labs. Now, a gas can also become a solid, and this is actually pretty useful in making different materials, which is something we'll see a little bit in Chapter 12. This is referred to as deposition, where molecules from the gas phase condense directly into the solid phase. Now, in addition to nomenclature here, there's energy associated with all of these transitions. So we have most people's favorite topic here is delta H, or enthalpy. So these are enthalpies, but they're also referred to as heats sometimes, so both terms used interchangeably. The heat of fusion is the term that refers to what's happening at the melting point or the freezing point. This is how much energy it would take to cause that phase change at that temperature. So if you have a solid and you want to melt it into a liquid, it would require adding this much energy. If you have a liquid, you want to freeze it into a solid, that would require removing this much energy. Now, I have some information here for a couple of different compounds. So the heat of fusion for water is 6 kilojoules per mole. And what that tells us is there's not a big difference in terms of arrangement between the solid and the liquid. So there's not a big energy dependence on changing from solid to liquid. In mercury, however, there is a fairly big difference in energy between the solid and the liquid. So you have to add more heat per mole of mercury in order to get solid mercury to melt, or you have to remove more heat per mole of mercury to get liquid mercury to freeze solid. There is another enthalpy associated with the transition between gas and liquid called the heat of vaporization, abbreviated delta H with the little subscript VAP for vaporization. For water, this energy is 41 kilojoules per mole, right? Very big compared to the transition from liquid to solid for water. And what that's reflecting is the strength of the intermolecular interactions you have in water. So we've seen hydrogen bonding in water. There's actually a pretty strong interaction between different water molecules as they're in the liquid phase and they're close together. We've got to break that interaction in order to boil the water. So it actually takes quite a bit of energy to break water apart and get it into the gas phase. This is also true of mercury. Now, mercury is atomic. It's just mercury atoms in there, but mercury is a very large atom, very polarizable electron shell. So even though this is just London dispersion forces, they're actually very strong, and it takes a lot of energy to convert liquid mercury into gas phase mercury. Now, if we start to look at taking a material and moving it through some different phases, we can look at something described as a heating curve. So I'm going to make a little graph here. On one axis, I am going to put temperature. So I'm just going to abbreviate it TEMP, but increase in temperature as we go up the axis, decrease if we were to go down. Now, across the bottom, I'm going to put added heat. So we're adding heat into our sample. And just because I'm well familiar with the boiling and melting points, this heating curve is going to be for water. And I'm going to put some numbers on the edge here where we would expect water to freeze and to boil. So this would be degrees Celsius on my temperature axis. Now imagine we start right here where we've got water, a sample of water, it's in solid phase, it's below 0 degrees Celsius. What's going to happen if we add heat to the sample? Well, what's going to happen if we add heat is that the temperature is going to go up. So we're going to see this line rise, but it's going to rise until we get to about 0. Now, we've seen this type of interaction before back in chapter 4 of our textbook, or sometimes it's chapter 5, depending on the version. The amount of heat that we add to this sample is going to be equal to the specific heat capacity of the material times the mass of the sample times how much the temperature changes. So when temperature is changing, we can always use this equation to relate the amount of heat with how much the temperature changed. We do need to know how big the sample is and how much, or what the value of the specific heat capacity of the material is. Okay, that's something we should be able to do. Once we get to 0 though, this curve is going to flatten out because now we're in the range of the heat of fusion or the enthalpy of fusion. And that means we've got to add energy into the system to cause the change in structure from the solid phase to the liquid phase. So we're going to have to add a chunk of energy, and as we're adding that energy, the solid water is going to transition to liquid water, but the temperature is going to remain the same. It's going to remain 0 degrees Celsius. Anytime we add energy in, it's going to go to that phase change, not to raising the temperature. Once all the liquid is melted though, the temperature is going to start to climb again. It's going to climb up to 100 degrees. So we're back in a range here where we could calculate what's going on here using the specific heat capacity. Liquid water is going to have a different specific heat capacity than solid phase water, so we'd have to keep that in mind and use the right specific heat capacity. Now once we get to 100 though, now we've got another phase change. So the curve is going to flatten out again, right? And this one is going to be quite a bit longer than the one we had down here from solid to liquid, and that's going to be a reflection of the differences in energy here. How much energy does it take per mole of water to cause this phase change? So much bigger distance here where the liquid water is transitioning into the gas phase water. However, once we've gotten all that to be a gas, if we add more heat, the temperature of the gas will go up. Now, what we're going to want to do is kind of look at calculations along these paths here. That's what we'll do in the next video.